All right, in the last video we talked about the basic understanding of extreme values, both absolute and local extreme values, and we talked about critical points or critical numbers. And so we want to connect that now to finding extreme values on closed intervals. And we start with something known as Fermat's theorem. This is not Fermat's last theorem, if you're familiar with that. That is something entirely different. But this is an important theorem for us nonetheless. If f has a local maximum or minimum at x equals c, then c must be a critical point. So we've been talking about critical points. So if we have a local max or min, it must occur at a critical point. But the inverse of this statement is not true. In other words, if we do have a critical point, where meaning what the derivative is 0 is undefined, that does not mean we have a local maximum or minimum at that point. So if we have a local max or min, it occurs at a critical point, but we can have cases where that's not true. And you can see that in these two cases, right? This is the graph of the cubing function, it looks like, right? X cubed, and or some vertical stretch of it at any rate. So, but at any rate, the derivative is 0 right there at 0, isn't it? There would be a horizontal tangent line there. But this function is increasing on its domain, and so this is neither a max or a min here, right? It's not a maximum because there's values anywhere in any open interval. It's not a local max, let me clarify. It's not a local or an absolute max. But on any open interval about 0, there's always values greater than the value of the function at 0. And at the same time, there's always values over here less than it that are less than that value. So it cannot be a local max nor local min. In this function here, right, we have what right there at 0? We have a vertical tangent line, which means the derivative is undefined. Again, clearly that point is not a local max or min. Okay. So Fermat's theorem, though, is very useful for us, and it will help us in listing the possible location for critical for local max or mins. But again, it's no guarantee that we have a local max or min. We could have a point like this or a point like this, when the derivative is 0 or undefined. Now, we talked about the extreme value theorem, which said if a function is continuous on a closed interval, then it has a max and min. This now is how we find those max and mins. So if we're on a closed interval with a maximum f of c and f of d, then these values, these locations rather, where these max and mins occur, are either going to be the endpoints themselves, a or b, or at critical points. That's it. The max or min occurs at endpoints or at critical points. And so basically, what you do is you simply find the critical points, and then you check the value of the original function, not the derivative, right, but the original function at the endpoints and the critical points. So in our last video, we looked at this particular function. I'll just have you go back and review that video. If you go back to the last video, we found the critical points to be -1 and 1 for this particular function. And so I will have you note, though, we're looking just in the interval from 0 to 3. So be very careful. You do not want to include the critical point of -1. It's not in this interval. It would be irrelevant. I'm looking for the max and min just between 0 and 3. You don't want to go back to -1 to check. So x equal 1 is the only critical point in this interval. And just see the previous video where we calculated these critical points. See the previous video, part 1. Okay, and so all we're going to do is, I like to just do a little table. I'm going to simply check the value of the original function at the endpoints. What are the endpoints? 0 and 3, and at the critical point. Right, so here's my endpoints. And this right here is our critical point. So pretty easy. I plug in 0 into this. Clearly I get 1. If I plug in 3 into the function, I get 3 cubed minus 3 times 3 plus 1. That's 27 minus 9 is 18 plus 1 is 19. And then I plug in 1. 1 cubed is 1. Minus 3 times 1 is negative 2. Plus 1 is negative 1. Okay? Make sure you go back to the original function p. Don't plug it into the derivative. If you plug it into the derivative, you know you got a critical point. You're either going to be 0 or undefined. And it doesn't tell you anything. You don't want to know what the derivative is. You want to know what the extreme values for the function are. All right. Once you've done this, here it is. Here's the hard part. One of these three numbers is your maximum. Can you figure out which one it is? What is the biggest number between 1, 19, and negative 1? Yeah, no, it's not really hard. It's easy, right? Your maximum is clearly 19. Now that's the maximum value. It occurs, notice, at an endpoint. It occurs at x equals 3. But the maximum is 19, not 3. That's the location of the maximum. And you could have a maximum on an interval occur more than one place. You might have 19 listed more than one time in this list. The minimum is clearly what? Negative 1. It's very important, though. You only check the endpoints and the critical points. Nowhere else. Just the endpoints and the critical points. That's all you need to do. Right? Now, we can take a look at this function just to confirm this, right? If I were to graph this function, so what do we have here? We have x cubed minus 3x plus 1. Whoops, I'm used to the old school version. X cubed minus 3x plus 1. And I'm going to open a window to help me see this. What should my window look like? What should my x min and x max be? 0 to 3, right? And what should my y min and y max be? Well, if I did my work right, my min has to be at least negative 1 and my max has to be 19. I'll do a minimum of negative 5 and a, whoops, that's my x scale. I don't want that to be negative 5. I'll do a minimum of negative 5 and a maximum of 20. Okay. And I'll put my y scale at 5, so my tick marks are only 5 apart there. Okay. And I'll go ahead and graph this. Okay. And you can see if I go and trace, when x was what? When x was 1, I was at my minimum. So I plug in 1, right? I'm right there at the minimum. You see that occurs at a critical point where the derivative is 0, right? The tangent line there is horizontal. The derivative is 0 there, meaning we have a critical point. So the minimum on this interval, right? Just on this interval, right? The function will continue, forever that way, but just on this interval. That's what we're talking about. The minimum on the interval is equal to negative 1. That's the y value. It occurs at x equal 1, but its minimum value is negative 1. And then what's the max? The max is 19, which occurred at the endpoint of 3. Right? So if I plug in x equals 3, I'm up there. Notice I'm at an endpoint. That's not a critical point. Okay, but that's how we can have it. We can have max and mins at the endpoints and or at the any critical point. Okay. Let's take a look at a second example. In the last video, we looked at, in fact, all these functions were looked at in the last video, so please make sure you've looked through that to see how to find the critical points. So for this function, if you remember, we found critical points of 0 and 3/2. Is 0 and 3/2, are those values both in this interval? Yeah. So we're going to include them both, right? 0 and 3/2 are both in this interval. And so what am I going to look at? I'm going to look at the original function, not the derivative, which we found in the last video. And I want to check endpoints, and I want to check the critical points. Okay. So at negative 32, what do I get? I get negative 32 to the 3/5 power, 4 minus a negative 32. Okay. Well, 4 minus a negative 32, that's going to be 36. I know that. What's happening here? What's the 5th root of negative 32? The 5th root of negative 32 is negative 2. And then I cube it. That's negative 8. So negative 32 to the 3/5 power is negative 8. And 4 minus negative 32 is positive 36. If I multiply those together, I get negative 288. What's the value of the function when x is 4? What's going to happen here? 0, right? What's the value of the function when x is 0? Well, 0 to the 3/5 power rather is 0. And then what about 3/2? So if I plug in 3/2, I'll have 3/2 to the 3/5 power, 4 minus 3/2. 3/2 to the 3/5 power, 4 minus 3/2 is 8/2 minus 3/2 or 5/2. Okay. Now, I don't know what 3/2 to the 3/5 power is. I mean, I guess I can cube it and write as the 5th root of 27/8. Okay, or, you know, maybe I could find... I'm not going to worry about simplifying this anymore, but this would be the exact value in terms of, you know, I'd like to see that. But of course, we can approximate this now as 3.189. If you use your calculator to approximate that. And it is crucial on the test and everything that you show the calculation of the derivative, find your critical points, and then when you're finding the maximums that you show this. I want to show the exact values. I want you to be able to evaluate functions, because calculators can give you these values. Some of you know how to use the max-min features in the calculator. That's not what I'm interested in. Right? And you can certainly check with those, but this is how we proceed. So again, I have negative 288, 0 twice, and 3.189. Which one is the largest? It's right here. So our maximum value is the 3/2 to the 3/5 times 5/2, which is about 3.189. The minimum, what's the smallest number? Well, clearly negative 288 is the smallest. Okay, and we'll take a look at this function too real quick. X to the 3 divided by 5. I think I can leave it up there like that, power, and then times 4 minus x. Okay, and what does my Windows setting want to be now? Well, so the big one is what, negative 32 to 4, I mean the entire interval, negative 32 to 4, and I'll do increments of 4 on my x-axis, and then my negative 288, let's go down to negative 300 or something, I don't know, up to this, which was 3.189. I'll go up to maybe 5, a little bit more than that, and I'll put 10 or something there. So, alright, it's going to take a while for this thing to graph, but you'll notice at the end point, right, where we were negative 32 here, there's negative 32 in the x axis. Kind of hard to see that on this particular screen. You can barely see that curve there, but the minimum is at negative 288. Now the interesting is what's happening up here in this corner. So I'm going to sort of zoom in on that. I'm going to instead of going from negative 32, I'm going to zoom in from, say, negative 4 to 4 change that to a 1, and I'll do negative 10 to 5 or something like that and see what we have there. Alright, here comes the graph. I don't know if you can see it's coming up towards the origin. Right. And resolution is just not very good. Let's see if I do this real quick. There's a little better. At 0, remember there was a critical point of 0. Remember the derivative was undefined there. What's going on right there at 0? There's a vertical tangent line right there. The graph is coming, the tangent line becomes vertical right at that point. Okay. The other point where the derivative was 0 was here, right, at 3 halves, 1.5. And what's the height of that? That's the 3.189 about, right? That's this quantity right here. That's our maximum. Okay. All right, a couple more to go. Now, this one I will go back to. We found the critical points for this function. If you remember, there was an infinite number of them, right? And we did all this crazy stuff here. If you remember how to do that, right? Infinitely many solutions. But notice in this problem, it's just on the interval from 0 to 2 pi. So on the interval from 0 to 2 pi, our critical points are what? Pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2. So the critical points here, t is pi over 6, pi over 2, 5 pi over 6, and 3 pi over 2. Okay. So again, we're going to just look at the value of the function for different values of t, right? The endpoints and the critical points. Endpoints and our critical points. So we've got 6 different ones to check this time. And g of t. Alright, let's see at 0. Well, sine of 0 is 0, cosine of 0 is 1, 1 squared is 1, 0 plus 1 is 1. Sine of 2 pi is 0, cosine of 2 pi is 1 again, 1 squared is 1, we get 1. Pi over 6, sine of pi over 6 is 1/2. Plus, cosine of pi over 6 is the square root of 3 over 2. But I'm squaring that. So I'm going to get, what, 1/2 plus squaring this, I get 3/4. Square root of 3 squared is 3, 2 squared is 4. 1/2 plus 3/4 is 2/4 plus 3/4 is 5/4, which is, 1.25. Okay, what about at pi over 2? Sine of pi over 2 is 1, cosine of pi over 2 is 0. Again, I get 1. 5 pi over 6. Sine of 5 pi over 6 is 1/2 again. Cosine of 5 pi over 6 is negative square root of 3 over 2. But I'm going to square that, and that's going to give me the same thing here, right? So I'm going to get back to 1.25 again. And then sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. What's our max? What's the biggest number showing in this table? 1, 1.25, and negative 1, 1.25. What's our minimum? Negative 1. So we have a max that occurs at a critical point and a min that occurs at a critical point. So both are local, absolute max and min. Both of them occur at critical points, not at endpoints. And that can happen, as was happened in this situation. Okay, this, again, I'll remind you, we did in the last video, we found the critical point. There was only one of negative 1/2. Domain was all real numbers, right? So negative 1/2. again, I'm going to look at the value of this function, different values of x, namely the endpoints, -1 and 0, and the critical point 1/2. By the way, in some problems, the critical point could be an endpoint. That's a possibility, and then you only check it once, obviously. But you want to make sure you check all the critical points in that interval. Make sure, again, the critical points are in that interval. If I had a critical point of 5, I would not use it here because it's between -1 and 0. All right, plugging in, I get -1 e to the -2, or negative e to the -2, which is the same as -1 divided by e squared. If I plug in 0, 0 times that is 0. And if I plug in -1/2 for x, I get -1/2 e to the what? 2 times a -1/2? -1. This is -1 divided by 2e. Now, what's the max? What's the biggest number here? Negative something, and 0. 0. What's the min? Well, one of these two things are. Now, you can just use your calculator and punch it in and see which is smaller, but think about this. They're both negative. They both have a numerator of 1. One has a denominator of e squared and one has a denominator of 2e. Which is bigger, e squared or 2e? E squared or 2e? Well, since e is about 2.7 something, 2e is smaller than e squared. E squared is bigger than 2e. But if e squared is bigger than 2e, then the reciprocal 1 over e squared is smaller than 1 over 2e, right? If I'm dividing 1 by a bigger number, it's smaller. So this is smaller in absolute value. This one here is larger in absolute value. So this is the more negative one, and so the minimum is -1 divided by 2e. And you can use a calculator to approximate that. Okay, so that's the way we find max and mins for continuous functions, right? We're guaranteed to have a max and min on a closed interval. Those values will occur at either endpoints or critical points. Okay, so we find the critical points and we check the function at the endpoints and the critical points, and then we just find the max or min in that list. That's all we do. Now, in closing, I want to just talk about something we're going to be talking more about, a little more advanced, with the mean value theorem, which Rawls' theorem is basically a special case of. But if a function is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, with f of a equal to f of b, under those conditions, there's at least one number c in that interval such that the derivative equals 0. And I want to just not prove this. I want to just draw, sort of reason through this by drawing some, what can happen, so to speak. So closed interval from a to b here, and f of a is equal to f of b. So let's say f of a has a some positive value above the x-axis. Over here at the same height then as b. So these are at the same height. Okay, f of a and f of b. Now, I want to draw a function, basically connecting these points, that's continuous. Okay, so no holes or gaps, jumps, no vertical asymptotes, right? And it's also differentiable. So differentiable means what? No sharp turning points, no vertical tangent lines. Right? Basically, continuous and differentiable means it's differentiable. Basically means it's smooth. There's no sharp turning points and no vertical tangent lines. So smooth and continuous tangent lines. So how can I draw such a function? Well, I mean, you can't have any holes or gaps or jumps or anything, and so I'm going to have to make some turns at least once, right? And the minute I do, though, what happens? What's the derivative at each of these points? Right? Derivative of each of these points is 0. Right? So there's C, we'll say C1, C2, and C3. Right? And this says there's at least one value of C. Again, you can have many, right? And you can draw it, as far as you want, but you got to come back down, right? Or coming down here, you got to come back up. Either way, you're going to have a point where you have a horizontal tangent line. Kind of makes sense. It's almost impossible if you think about trying to draw such a function, because again you can't have a sharp turning point, right, where the derivative is undefined, because it has to be differentiable, or any kind of a vertical tangent line or anything crazy like that. And you can't have a vertical asymptote, it's continuous, and so there we have it. Now we're going to look at something called the mean value theorem in the next section, and that will be elaborating more on this theorem here. Okay, so that's it for this section.